So, I get to see a lot of new tech. Smartphones, laptops, electric vehicles, the stuff that's hitting the market right now or in the next year. But every once in a while, you hear about a category of technology that feels like it's straight out of a sci-fi movie. It's not just an incremental update, it's a fundamental shift in how we build things. And that's what we're talking about today. Emerging metadevices and their real-world applications. This isn't just about a faster chip or a bigger battery. It's about manipulating physics in ways that were previously just theoretical. These aren't just lab experiments anymore. We're starting to see these innovations shaping the future of technology, energy, and healthcare in some pretty profound ways. Imagine materials that can steer radio waves without any moving parts, antennas that can intelligently reshape themselves, or windows that are basically invisible thermal shields. These are metadevices, and they're built from metamaterials, engineered structures designed to have properties not found in naturally occurring materials. They're designed at a microscopic level to control waves, whether that's light, sound, or radio frequencies. And the applications are huge. We're talking about everything from making self-driving cars safer, to providing high-speed internet anywhere on the planet, to creating ultra-efficient clean energy solutions. This is the kind of deep-level, foundational tech that enables the next generation of gadgets and infrastructure. It's the stuff that happens behind the scenes, but its impact is going to be massive. So today we're going to dive deep into 7 of these meta-devices that are starting to break out of the lab and into the real world. This is the future, being built right now. Alright, so first up is something that sounds incredibly complex, but the idea behind it is pretty clean. It's called an RF beam steering module, with a metamaterials electronically scanned array, or MESA for short. Now think about a traditional satellite dish or a radar system. To point a signal, you physically have to move the dish. It's mechanical, it's slow, it can wear out, and it's bulky. MESA completely changes that game. It's a flat panel, no moving parts, that can steer a radio frequency beam just by applying different voltages to its surface. The magic here is in the metamaterial structure. It's covered in tiny, individually tunable elements that act like a phased array. By controlling the electronic properties of these elements, you can change the phase of the radio waves passing through them. This allows you to precisely aim the beam in any direction, almost instantaneously. It's like having thousands of tiny antennas all working together in perfect sync. The result is a system that's not only faster and more reliable, but also significantly smaller and lighter than its mechanical counterparts. It's a solid-state solution to a mechanical problem. So, where does this get used? The applications are huge. For self-driving cars, MESA can power next-gen LiDAR and radar systems, giving the car a 360-degree view that can track hundreds of objects at once without any spinning parts. For communications, think about broadband satellite internet. Companies like Starlink need to connect moving satellites to stationary users on the ground. MESA technology makes those ground terminals flatter, cheaper, and more efficient. It's also a key enabler for advanced 5th and 6th generation networks, allowing for more focused and efficient data transmission, which means faster speeds and more reliable connections for everyone. Sticking with the theme of communications, let's talk about antennas. The antenna on your phone or in a cell tower is usually a one-size-fits-all kind of deal. It's designed to work, but it's not necessarily optimized for every single situation. What if an antenna could change its properties on the fly to give you the best possible signal at all times? That's the idea behind smart metamaterial antennas. These aren't just static pieces of metal. They are highly reconfigurable systems that can adapt to their environment in real time. These smart antennas are built with metamaterials that can be electronically tuned. Think of it like a liquid metal antenna that can reshape itself, but without any actual movement. By applying control signals, the antenna can change its frequency, radiation pattern, and polarization. Is there a lot of interference coming from one direction? The antenna can create a null in its pattern to block it out. Do you need to focus a strong signal on a specific user far away? It can form a narrow, high-gain beam. It's an incredibly dynamic and intelligent way to manage the radio spectrum. The impact on our wireless world is pretty obvious. For 4th and 5th generation base stations, this means a massive improvement in efficiency and capacity. Instead of blasting a signal out in all directions, the tower can create dedicated beams for individual users, reducing interference and boosting data speeds. This is crucial as more and more devices come online. For satellite communications, reconfigurable antennas on the satellites themselves can adjust their coverage areas based on demand, directing bandwidth to a crowded city during the day and shifting it to residential areas at night. It's about making our wireless infrastructure smarter, not just bigger. Okay, so we've talked about sending signals, but what about power? Specifically, powering the billions of tiny devices that make up the Internet of Things, or IoT. You can't run a power cord to every sensor in a smart building or on a remote bridge, and changing batteries in billions of devices is a logistical nightmare. The solution is energy harvesting, pulling power from the ambient environment. And you guessed it, metamaterials are making this process way more efficient. The idea is to capture wasted energy that's all around us. This could be stray radio waves from Wi-Fi and cell signals, or it could be tiny vibrations from traffic or machinery. The problem is that this ambient energy is usually very weak and spread out. Standard energy harvesters are often inefficient because they can only capture a small fraction of it. This is where metamaterial enhanced energy harvesting comes in. These devices use metamaterials to act like a funnel, concentrating ambient energy into a single point where it can be converted into usable electricity. For example, an electromagnetic energy harvester can use a metamaterial lens to focus radio waves from a wide area onto a small rectifying antenna, dramatically increasing the amount of power generated. Similarly, a vibroacoustic harvester can use a metamaterial structure to trap and amplify mechanical vibrations at a specific frequency, turning even subtle movements into electricity. The end goal is to create self-powered IoT sensors that can operate for years without maintenance. This is the key to unlocking truly massive IoT deployments for smart cities, industrial monitoring, and environmental sensing. It's a quiet revolution in how we power the smallest of tech. Shifting gears from communications and energy to healthcare, this next one is genuinely mind-bending. It's called Focused Magnetic Stimulation, or FMS. Now, techniques like transcranial magnetic stimulation, TMS, already exist. They use magnetic fields to stimulate nerve cells in the brain to treat conditions like depression. But honestly, the current technology is a bit of a blunt instrument. The magnetic fields are large and diffuse, making it hard to target specific small areas of the brain without affecting the surrounding tissue. FMS uses metamaterials to solve this problem with incredible precision. The device uses an array of micron-scale coils, basically these tiny electromagnets, embedded in a flexible substrate. These coils are the meta-atoms of the metamaterial. By controlling the current in each of these microscopic coils individually, you can shape the magnetic field with, honestly, unprecedented accuracy. You can create a highly focused point of stimulation deep within the tissue, or you can generate complex dynamic patterns of stimulation across a larger area. The level of control is on a whole new level. We're talking about improving depth control and spatial resolution by an order of magnitude. This could revolutionize neuroscience research by allowing scientists to study brain circuits with much higher fidelity. Clinically, it could lead to more effective and targeted treatments for a range of neurological and psychiatric disorders, from Parkinson's disease to epilepsy, all with fewer side effects because you're only stimulating the exact cells that need it. It's like going from a floodlight to a laser pointer for brain stimulation, and it's a huge leap forward. Alright, let's talk about waste, specifically waste heat. In power plants, in car engines, in industrial processes, a massive amount of energy is lost as heat that just dissipates into the atmosphere. What if we could capture that heat and turn it directly back into electricity? This is the promise of thermophotovoltaics, or TPVs. It's kind of like a solar cell, but instead of converting sunlight, it converts thermal radiation, light in the infrared spectrum, into power. The problem with TPVs has always been efficiency. A hot object emits light over a very broad spectrum, but a photovoltaic cell can only efficiently convert a narrow band of that light into electricity. All the other frequencies are just wasted, or they heat up the cell and make it even less efficient. This is where spectrally selective metamaterial emitters come in. You place this metamaterial on the surface of the hot object, and it acts as a filter, fundamentally changing the way it radiates heat. Instead of emitting a broad, messy spectrum, the metamaterial emitter is engineered to only radiate light at the exact frequencies that the photovoltaic cell is best at converting. It suppresses all the unwanted thermal radiation and channels all that energy into a narrow, useful peak. This simple-sounding trick dramatically boosts the overall efficiency of the system, making TPVs a much more viable technology. The potential here is to create solid-state heat engines with no moving parts that could be used for waste heat recovery in factories, or even for ultra-efficient home power and heating units. When you think of insulation, you probably think of that thick pink stuff in your attic or the foam in your walls. It's bulky, it's opaque, and it works by trapping air. But what if you wanted to insulate something that needs to be transparent, like a window? This has always been a huge challenge. You can add coatings or have multiple panes, but you're always trading insulation for clarity and adding weight. A new class of Metadevices, a transparent aerogel polymer, is set to completely change this. This material has achieved a record-low thermal conductivity for a transparent substance. It's essentially an engineered foam at the nanoscale, a solid but mostly empty space. The structure is so fine that it's smaller than the wavelength of visible light, which means light passes right through it without scattering. So, to your eye, it looks like a perfectly clear piece of glass or plastic. But to heat, it's an incredible barrier. The nanoporous structure is extremely effective at stopping heat transfer, both conduction and convection. The applications are pretty straightforward and incredibly impactful. Imagine single-pane windows that insulate as well as triple-pane windows, but are lighter and cheaper. This could dramatically reduce heating and cooling costs for buildings. You could apply it to skylights, greenhouses, or even the canopies of electric vehicles to reduce the load on the climate control system and extend their range. It's a thermal barrier you can see through, a metamaterial that solves a very fundamental and universal problem in architecture and engineering. It's a simple concept with a very complex and clever execution. So for this last one, let's talk about cooling. Air conditioning uses a massive amount of electricity, contributing significantly to energy consumption and carbon emissions, especially in hot climates. It's an active process. You use power to pump heat from inside to outside. But what if a material could just get cold, all by itself, even under direct sunlight, with zero energy input? This is not science fiction. It's a real technology called passive radiative cooling, and it's enabled by a new class of scalable metamaterial films. Here's how it works. Every object radiates heat. The key is to design a material that does two things perfectly. First, it has to be an almost perfect mirror for sunlight, reflecting over 97% of the light that hits it so it doesn't heat up. Second, and this is the metamaterial trick, it has to be a perfect emitter in a very specific infrared window. There's a transparency window in Earth's atmosphere, where infrared radiation can pass straight out into the cold of deep space without being absorbed and re-radiated back down. This film is engineered to radiate its own heat out through that exact window. The net effect is that the film is constantly sending more heat out into space than it's absorbing from the sun, allowing it to cool down to several degrees below the ambient air temperature, even in the middle of a hot, sunny day. You can make these as large roll-to-roll films, or even as paint-like coatings. You could coat the roof of a building, and it would passively cool the entire structure, drastically reducing or even eliminating the need for AC. You could use it on power plants to improve their efficiency, or even in desert applications to cool water or shelters without any electricity. It's a truly game-changing sustainable technology. So, from self-steering antennas and power-harvesting surfaces to pinpoint brain stimulation and self-cooling films, it's clear that we're at the beginning of a major shift. These emerging meta-devices are redefining what's possible in technology, energy, and beyond. They're not just incremental improvements. They represent a new paradigm in engineering, where we design materials from the atoms up to have exactly the properties we want. It's a fundamental change in how we interact with the physical world, controlling light, sound, heat, and electromagnetic waves in ways we couldn't before. The 7 examples we looked at today are just the tip of the iceberg. The underlying principles of metamaterials are being applied by researchers to solve problems in almost every field imaginable. While some of these technologies are still a few years away from being in the products you buy, they are the foundational building blocks for the tech of the future. The smart city, the truly autonomous car, the next generation of wireless communication, and breakthroughs in sustainable energy. All of them will be enabled in part by these invisible but powerful innovations. It's the kind of stuff that gets me really excited for what's next. We'll definitely be keeping a close eye on this space as these devices move from the lab to the mainstream. So, if you're into this kind of deep dive tech, it's a good time to be paying attention. As always, thanks for watching, and I'd be curious to hear which of these you think will have the biggest impact down in the comments. Stay tuned for more innovations, and I'll catch you in the next one.